The triangle is one of the building blocks of geometry. We will review information in this lecture about the importance of triangles, the various parts of a triangle, the classifications of triangles, and triangular relationships, including trigonometry. From the earliest study of geometry, the triangle was extremely important. Much time was spent by scholars investigating the triangle. A triangle is a simple shape. It is the polygon with the fewest number of sides. As was demonstrated in the previous lecture, the triangle is the building block for all polygons. Each time we add a side to a polygon, we add a triangle, or 180 degrees, to the interior. As we demonstrated, the triangle is rather important, but also it's important in terms of construction. The triangle is a very stable shape. It is used in all types of construction because of its stability. The next time you cross over a bridge, if the bridge has structures up the side, check out the structure and you'll see triangular shapes because the triangle is exceptionally stable and is useful at holding things up that you don't want to fall down. The Pythagorean theorem has elevated the importance of the right triangle. Again, a very special type of triangle. Triangulation has been used to measure distances for thousands of years. We'll talk more about that later on. The shape of the Greek letter delta is a triangle. And we can see the Greek letters written out, delta, and the English word delta. And of course, the word delta means the end of a river. When a river is about to go into the ocean or sea, and it forms a triangular shaped piece of land where the water breaks up and flows to the body it's flowing into, that is the delta. So the Nile Delta, for example, or the Mekong Delta, the word comes in effect from the notion of the triangle. It is known that the sum of the three angles of any triangle is 180 degrees. No matter what the shape, what the size of that triangle is, it is always 180 degrees. The largest angle of a triangle is always opposite the largest side in that triangle. The smallest angle is opposite the smallest side, leading the middle-sized angle opposite the middle-sized side. And of course, if we have two angles in a triangle that are the same, the sides opposite them must be the same. If the two sides, all three sides are the same, then all three angles are the same. In fact, an equilateral triangle is equiangular. The triangle could be called a trigon because it has three sides. Gon meaning side, polygon meaning many-sided. And of course, it's called a triangle because it's called a triangle because it has three angles. Let's take a look at some of the various types of line segments existing in a triangle. The first is the altitude or height. This is the distance from the vertex at the top of the triangle to the base at the bottom of the triangle, provided that that line segment is perpendicular to the base. So therefore, we could also say that the area of a triangle is 1/2 the base times the altitude. Another important line segment is the angle bisector. The angle bisector is a line segment starting at the vertex that ends at the base and bisects the vertex angle into two equal angles as shown. A perpendicular bisector is an angle bisector that is perpendicular to the base. And notice it also bisects the base. So we have a triangle with a perpendicular bisector. It bisects the angle of the vertex, is perpendicular to the base, and assuming the base is 8 units measurement, it divides the base into two line segments, each of measurement 4. The median is a line segment from the vertex to the base that divides the base into two equal pieces. You can say, well, why isn't the median a perpendicular bisector? Well, sometimes it can be, but notice in this case, this median is not perpendicular to the base, and therefore it can't be called a perpendicular bisector. So the more generic line segment is the median, one from the vertex that bisects the base. And finally, we have the midsegment. The midsegment is simply a line segment from the midpoint of one side of a triangle to the midpoint of the other. In fact, we talked earlier in Lecture 12 about fractals, and we talked about the Sierpinski triangle. We actually were connecting the midpoints of the three sides of an equilateral triangle. In the diagram here, we have a triangle that has a side of 14 and a side of 12. We have found the midpoint, dividing the one side of 14 into two line segments equal to 7, and the other line segment, the other side, into two line segments of 6 each. Connecting those midpoints, we have a mid-segment. Now, triangles can be classified in various ways. Primarily, we look at the types of sides, or the relationships of the sides, or the types of angles in the triangle. So here we see three classifications of triangles by angle. And any triangle you construct must be one and only one of these three types. We have the obtuse triangle. This is a triangle whose largest angle is greater than 90 degrees and less than 180. Obviously, the sum of the three angles must be 180. So if one angle is obtuse, greater than 90, the other two angles must be acute. Acute meaning less than 90. It's really easy to remember these names if you have trouble. Acute means sharp, and an angle that's between 0 and 90 is quite sharp, while an angle between 90 and 180 is quite dull. And in fact, someone who is dull is called obtuse. And of course, one angle that is exactly 90 degrees is a right angle. So a triangle that has a right angle is called a right triangle. And once again, since the sum of the two angles of any triangle must be 180, if one of those angles is a right angle, the other two angles must sum to 90, which means each one must be acute. If all three of the angles in a triangle are acute, then that triangle is said to be acute. So we have an obtuse triangle, a right triangle, and an acute triangle. Probably the easiest way to determine which type it is to find the largest angle in the triangle. If it's obtuse, then the triangle is obtuse. If the largest angle is a right angle, it's a right triangle. And of course, if the largest angle is less than 90 degrees and is acute, the triangle is labeled acute. Let's take a look at how we classify triangles by their sides. If all three sides are the same, are congruent, we have an equilateral, equal sides, equilateral triangle. If two of the sides are the same and the third side is different, we have an isosceles triangle. If all three sides are different, we have a scalene triangle. So again, we have three classifications of triangles by their sides. Scalene, all three different. Isosceles, two sides the same. And equilateral, all three sides are the same. Let's take a look at the relationships between types of triangles. For example, can you have an obtuse triangle that is equilateral? And the answer is no. In an equilateral triangle, all angles and sides are the same. If all angles are the same, they must equal 1/3 of 180, which is 60 degrees. And therefore, an equilateral triangle must be acute. But a isosceles triangle can be obtuse, it can be right, and it can be acute. And of course, a right triangle cannot be equilateral. A right triangle can be isosceles, and it can be scalene. Now let's take a look at the relationships between the size and the shape of two triangles. Two triangles that have the same shape but different sizes are said to be similar. This is quite important because when we draw scale drawings or make scale models, we are looking for shapes that are the same shape but different sizes. When we draw a map to scale, we are looking for a map the size, let's say for example the distance between two cities in inches, tells us the distance between the actual cities in miles or kilometers. And since triangles were the earliest shape that was investigated thoroughly, similar triangles were quite important in the development of scale drawings and scale models. Two triangles are similar if they have the exact same shape. The angles of the triangle establish this shape. So we can say of all corresponding angles, a corresponding angle is an angle in the same location in one triangle as in the other. If all corresponding angles are congruent, then the triangles are said to be similar. We need know nothing about the sides to prove two triangles similar. All we need to know is all three angles are the same. Now, if you're really paying attention, you might understand as, now wait a second, if I know two of the angles of a triangle, since the sum of the three angles must be 180, I immediately know the other angle. And that's correct. So really, all you need to know to prove two triangles similar is that two corresponding angles in one triangle are the same as the two corresponding angles in the second triangle. And this is called the angle-angle proof for triangular similarity. There are two other proofs indicated on your screen. SAS is side, angle, side. We know that the sides of similar triangles, that is corresponding sides, are in proportion. They maintain the same ratio. So if one triangle has sides that are twice the other, twice the corresponding sides in the other triangle, then we have similar triangles. So if you can find two sides in one triangle that have the same ratio in relationship to the corresponding sides in the second triangle, and the angle in between those pairs of sides is the same. The angle in one triangle and the corresponding angle in the other triangle are the same. We have side, angle, side, proof of similarity. The third is labeled SSS, side, side, side. This proof requires that corresponding sides, all three sets of corresponding sides in the two triangles, have the same ratio. So if one triangle has a side of 10 and its corresponding side in the other triangle is 5, then we know that the ratio is 2 to 1. So in the larger triangle, a side is 8. The corresponding side in the smaller triangle would be 4. If all three corresponding sides are in the same ratio, we have a side, side, side proof of similarity. And this again goes back to the notion of proof first developed as deductive reasoning by Thales in ancient Egypt. It's also the kind of proof that one sees in a high school geometry class. Now, if two triangles have exactly the same size and the same shape, they are said to be congruent. That is, they are exactly the same. Similar triangles are the same shape but not the same size. So congruent triangles, in reality, are similar triangles that are identical in terms of size and therefore have the same area. There are various ways of proving two triangles congruent. Let's look at a list of those ways. We have side, 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 SSS. That means you must show that corresponding sides in one triangle are exactly the same as the corresponding sides in the second triangle. And once you have shown that, you know that each triangle is the same shape and the same size, and therefore the two triangles are congruent. SAS, again, it means side, angle, side, but unlike in the similarity proof, where you're involved in proportional nature of the sides, here you must have two sides that are identical to the two corresponding sides in the other triangle, and the angle between those two sides in each triangle must be the same measure. So we have side, angle, side. Our next proof would be a proof involving two angles and a side. This is the angle, side, angle proof. If you have two corresponding angles with the same measure, so that, for example, in triangle 1 we have an angle of 40 degrees, and in the second triangle a corresponding angle of 40 degrees, and angle 2 in the first triangle is, let's say, 70 degrees, and the corresponding angle in the second triangle is 70 degrees, we would have two angles that are congruent. If the side in between them was congruent to its corresponding side, we have an angle-side-angle proof. Now, of course, if we knew two angles and one side in the triangle, and those two angles were not the two angles that surrounded, if you will, the side, we still have an angle-side-angle proof, because knowing two angles, we know the third angle must be the same. And therefore, we can talk about an angle-angle-side proof, which is really another version of the angle-side-angle. Finally, if we have a right triangle, we know we have two right triangles, therefore we have an angle in each triangle that is the same, the right angle. And if we know that one of the legs is the same as the corresponding leg in the second triangle, and the hypotenuse of the first triangle is congruent to the hypotenuse of the second triangle, we have a proof of congruence called hypotenuse leg. Now you'll notice that we have a side and an angle, but it only works for right triangles. If you have a triangle that is not a right triangle, and you have two sides and the angle, but the angle is not included between the two sides, this is not a proof of congruence. Not at all. And therefore, we do not have a side-side angle proof on our list. Okay? So we've looked at similar triangles, we've looked at congruent triangles, and those triangles were used initially to begin the process that led to the use of trigonometry. Trigonometry literally means measuring with triangles. Trigonometry. A trigon is a triangle. Metry means to measure. Knowledge of triangles have been used since ancient times to enhance the ability of humans to measure. Knowing about similar triangles allowed people to come up with ratios between corresponding sides, so that one could measure various things by using ratios of similar triangles. In the 13th century BC, Egyptian mathematicians wrote about the use of shadows and proportional triangles to tell time. And we've seen that before. Of course, it's called the sundial. Using triangles to measure distances was recorded in Mesopotamia in 1000 BC, in Greece and in China in 500 BC, and in Sanskrit writings in India in the year 100 AD. So in all cases, those societies used triangles to measure distances. Triangles were used to measure distances for navigation, but no formal study of the triangular relationships existed until the 6th century AD. In the year 500, Indian mathematicians studying ideas about triangles, written by ancient Greeks and Babylonians, began to develop the current science of trigonometry. Okay? They started with a circle. Notice the circle has a radius of 1. And we've drawn a radius that is perpendicular to a line segment between 2 points on the circle. That line segment is known as a chord. So we have a radius of 1, we have a radius that is cutting through a chord, and geometry tells us that when a radius is perpendicular to a chord, it bisects it. So now we have a triangle, a right triangle, with the right angle, whose hypotenuse is 1, and whose side opposite the angle formed by the radius that is 1 and the other radius that is perpendicular to the chord is a half chord. And the angle that we're talking about is called a central angle, since its vertex is the center of a circle. So we have a right triangle with an angle, central angle, opposite a side that is a half a chord. And this was called a half chord. The ratio of that side, opposite to the angle, over the hypotenuse, which we know is 1, was called the half chord, because the distance, half chord divided by 1, is half chord. And therefore, this ratio for any angle was called the half chord. The opposite to the hypotenuse, that ratio was called by the people in India the half chord. Since all right triangles with an acute angle equal to a specific central angle would be similar to the triangle in the circle, the ratio of the opposite to the hypotenuse for any similar triangle, any triangle with the same angle, was known. When the Arabs invaded India, they discovered the work being done on trigonometry and adapted it for their own use. The name half chord was translated into Arabic. When this knowledge reached Europe, the Arabic word was mistranslated into the Arabic word for cove, and the Latin word, of course they used Latin since most scholarly writings were in Latin, the Latin word for cove is sinus, S-I-N-U-S. Thus we call the ratio between the opposite and the hypotenuse the sine of the angle, in a right triangle, of course. Now, you'll notice we see here a right triangle. We have its opposite, its hypotenuse, and the third side, the side that is not opposite the angle in question and is not the hypotenuse, is called the adjacent. The opposite and the adjacent are the two legs. They form the right angle. And we have the sine is the ratio of the opposite to the hypotenuse. Now, this thing called the cosine, its name is very simple to understand. If we look at the angle that is not the angle in question, that is the angle formed by the hypotenuse and the side we've labeled opposite, that angle must be the complement of the other angle. And the reason is those two angles need to add to 90 degrees since the sum of all three angles is 180. So the sine of the complement is the adjacent over the hypotenuse, and the complement sine was shortened to cosine, thus the name cosine for the ratio of the adjacent to the hypotenuse. If we have a right triangle, as pictured in the next image, formed by a tangent line, that is a line that touches the circle only once, and a secant line, a line, if extended, that will cut the circle twice. And the third side of that right triangle is a radius of the circle, and the circle has radius 1. We have a right triangle. How do we guarantee that that's a right triangle, that that angle formed between the tangent and the radius is perpendicular, is 90 degrees? Well, geometry tells us that in any circle of any radius, where a radius meets a tangent line at the point of tangency, it is perpendicular. This was something that Euclid knew hundreds of years ago. So we have this triangle. If we look at the angle formed at the center, the central angle, and we look at the opposite over the adjacent, the opposite is the tangent line. The adjacent is the radius 1. So the ratio is the tangent over 1, which is tangent. And therefore, the ratio in trigonometry of the opposite to the adjacent is called the tangent. Similarly, the adjacent over the opposite is the tangent of the complement angle. It's the complement's tangent, or the cotangent, adjacent over opposite. If you look at the ratio of the hypotenuse to the adjacent, at a secant over 1, and the relationship secant over 1 obviously is equal to the length of the secant, and therefore the ratio of hypotenuse to adjacent is called the secant. Now, I know in school, in high school, when I learned about the trig ratios, it bothered me that the secant was hypotenuse over adjacent and not hypotenuse over opposite. But the reason for that was because hypotenuse over adjacent is exactly the ratio of secant to the radius of 1. The cosecant, the secant of the complement, is hypotenuse over opposite. And these are the 6 trig ratios that were discovered through the use of right triangle trigonometry, or right triangle relationships in India, and adopted in the Arabic countries, and eventually used in the European countries to develop more uses of trigonometry in terms of looking at trigonometric functions, which we'll talk about briefly soon. With tables of trigonometric values, measurement was accomplished. The heights of trees and mountains was obtained. The distance across a river or a canyon could be measured using the tangent ratio. The distance from a location of a cannon to the wall of a city that was under attack could be measured using sine or tangent. The angle required for a ramp could be measured using any trig ratio, depending on which sides of the ramp you knew. The length of a road for a certain grade, a certain elevation on a highway, could be calculated using sine or cosine. So the trigonometric ratios became very important. But also, as I previously said, they can be used as functions. And to do that, we need to look at the graphs of the sine and the cosine. So let's go to the TI-83. This is the graph of y equals sine x from negative 2 pi radians, or negative 360 degrees, to positive 2 pi radians, or positive 360 degrees. Notice the shape. Let's start at x equals 0. The sine wave increases, reaches a maximum at 90 degrees, returns to the x-axis, then goes negative, and returns positively to the x-axis at 360 degrees. This sine wave is repeated over and over again. The visualization of the sine function allowed people to develop models for things that oscillated. Let's take a look at the cosine function next. This is the graph of y equals cosine x. You'll notice it is also a wave form, but looks a bit different than the sine wave. If we start at 0, you'll notice that the cosine is maximized, a value of 1. And as x increases, the cosine value goes down to 0 at 90 degrees, continues until it's negative at 180 degrees, and then rises up again to max out at 360 degrees and start the wave all over again. Now, if you look carefully at that cosine wave and visualize taking it and moving it, pushing it to the right 90 degrees, you will see that we have a sine wave. So the sine and the cosine really are the same, except they're out of phase. Something that becomes very, very important. We're talking about models of oscillating occurrences. Thus, we can see that the sine and cosine functions can be used for things that cycle or oscillate, such as what? Well, one of the earliest uses was indeed the pendulum. Remember, at one point in time, other than using a sundial or a water clock, clocks were driven by a pendulum. And Galileo did a lot of work with pendulums, and indeed the movement of the pendulum back and forth, can be modeled by a sine or cosine wave, because the pendulum reaches a maximum in one direction, goes through the neutral position where it would be resting, and then rises up in the other direction to an extreme negative, back and forth, and continues in that way. And of course, that would be a sine or cosine wave. You say, wait a second, a pendulum eventually slows down, and if you don't wind the spring, it stops. In that particular case, you have what's called a damped sine or cosine. A sine or cosine wave with each succeeding cycle is a little bit shorter in height than the preceding one until it basically goes to 0. Still, it's a sine or cosine wave. Business and agricultural cycles can be modeled using a sine or cosine wave. These waves are both called sinusoidal functions. Sound, light, and radio are waveforms and can be seen on an oscilloscope as a sinusoidal graph. Seasonal changes, such as temperature and rainfall, which cycle, can be modeled with sinusoidal functions. Unfortunately, the tangent, cotangent, secant, and cosecant functions are not continuous. They have gaps and jumps, and therefore are not very useful, as the sine and cosine are, as models for real-world situations. In our next lecture, Lecture 16, we will talk about additional geometric shapes in a topic of conic sections.